Yeah, okay. I guess it's online now. Okay, so do we start?
Yes.
Okay. So, okay, can I have some okay, is that everyone in the room right now?
Yes.
Okay, so I just have like a few questions
Yeah.
before I start. So, can you guys just tell me something about yourself, like who's there right now?
Starting with uh, hi Suchakra. This is Gaurav.
Yeah.
Work with Veritas. It's mostly in storage software. So I'm interested in Linux kernel. So I've started attending the reserve with Meetup. I read a couple of your papers. I didn't understand anything of it, but I
Papers
tried.
as in research papers?
Yeah, yeah. I
Oh
saw
my
that,
God. Okay.
but I didn't understand anything. So
Yeah, it's okay. I mean, I also don't understand them. Okay, I'm joking. Okay, that's good to know. So you have started just in the Linux kernel stuff, or have you already, like tried to go through the code and things?
no, I've just started. So as of now, I'm trying to read some books and probably just go through the old 2.6 code. So just
Okay, okay. Yeah, and next.
that's it. Hi, my name is also Gaurav. I'm a final year,
Oh,
I'm a final year student. Currently, I'm interested to learn more about kernel. So currently, I don't know where to start. But yeah, sure.
okay, okay,
Yeah.
okay.
To begin with, I would like to know more. Think
Yeah,
I
I'll try to make this a bit introductory, so I guess it's okay. Thanks. Thanks, Gaurav.
Hi, I'm Amit, and I have been working on the kernel for roughly 10 years. So, yeah, so mostly on power management, parts of the network stack. I have commits in the kernel. So, I'm currently working on embedded Linux mostly.
Okay, okay. Nice to know, Amit. Yeah, you are a pro, so you know more than me actually. Okay, thanks.
Hi, I'm another Amit Garge.
Okay. Yeah, two Gauravs and two Amits. Okay.
Yeah, actually, I'm working on the Python automations, and I'm using Linux for more than 4 to 5 years.
Okay. So
So that,
you're definitely gonna enjoy this session, Amit, because there's some Python stuff to it also.
yeah, so actually, I saw a lot of the automation script in the Linux related project. So that will be helpful to developer to make videos.
Okay.
Yeah, and I'm firstly started only color compilation and installation, just like latest stuff. So I only know the basic knowledge of Linux kernel.
Okay. Okay. Thanks, Amit. So I guess I know you two guys, so we can probably start. Does that sound like a plan?
yes, because everyone here also knows each other.
Okay. So I'm just gonna share my screen. Okay. So I'll start this session with a small, quick introduction to eBPF and what is BCC. So it seems to be the hype of the day. And I guess I'll try to cover as much as possible without going too much in depth so it becomes boring for introductory sessions. So I'm Suchakra. This is my full name, Suchakra Pani Sharma. And I work in this company called Shift Left as a scientist. And I've been involved with BCC and iVisor project. And I completed my PhD from Polytechnic Montreal, University of Montreal. And I had to do a lot of this stuff during my PhD. And that's why I got a chance, and it was kind of an opportunity to look at the kernel code in depth and in this section. So, as you guys know, kernel is pretty vast. So, and I don't understand all of the parts of the kernel, but definitely some of the parts which I really find interesting. So this is going to be the session about eBPF and BCC. So what is eBPF? So the full form is Extended Berkeley Packet Filter. It was essentially called as BPF, Berkeley Packet Filter, and then there was some extensions as in like some new things added to it. The architecture was changed a little bit. It became more generic, and now it has evolved to be a stateful, programmable in-kernel decisions for networking, tracing, and security. So I came up with this. So basically, what it means is that for networking, tracing, system tracing, and for security, you now have a way to uh, statefully define your programs and maintain states in the programs and generate outputs from those. So it can be used for networking in the sense that you have something new called as express data paths. You can use it in traditional manner for network packet filtering. And for tracing, you can use it to hook onto any kernel functions. You can hook onto static trace points defined in the code, and you can get that data out through perf or through trace events. You can also use it to use it for security using some upcoming patches, or I guess they are already there, which allow you to define what syscalls to allow and what syscalls to not allow. So this was actually already there as part of seccomp, but seccomp is not using the new eBPF. The new eBPF version patches are called as landlock LSM. So they use the traditional Linux security modules techniques such as SE Linux and I don't know, App Armor, and they are a bit different from LSM, but it basically allows you to program your security. So so what is eBPF? So we first start with classical BPF, which is now called as CBPF in the Linux kernel. It's based on a research paper by McCain in 1993, and I don't know the second author. I forgot the name. So basically, it allowed you to do network packet filtering inside the kernel. So they moved the part of filtering from copying the buffers to the user space and doing there to doing it inside the kernel, and that too with a very nice register-based machine. So it was a small VM which would run inside the kernel, and you would compile the BPF bytecode for that VM, and you will send it to the kernel, and then the kernel interprets that bytecode and makes decisions. This was also extended in Linux kernel for seccomp, which is secure computing. And I guess I to just give you like a high-level example. If you have used Chrome browser before, then you have definitely used seccomp. So so yeah. So yeah, I told you about the small in-kernel VM part. It's a register-based VM, and it has a very simple switch dispatch interpreter, which means that like you have a switch case which just takes in the incoming bytecodes and says, okay, we have to do this, and it just executes that. So CBPF was then later on extended, I guess in 2014 or 15, December 2014 or 2015 by Alexei. Um, and what he did was to take that BPF from a traditional networking use case and take it out and make it more generic. So it became like a small, not a subsystem, but a small section of the kernel in itself, which everybody else can use that. So it got more registers. There are, I guess now 11 registers, R0 to R11, and previously there was just 2 registers. They would use in a scratch space, memory space in the VM. There is now a JIT compiler. There was a JIT compiler before also, but now they have a faster and more flexible optimized JIT compiler. There is a verifier which verifies the incoming bytecode. And now there are facilities to attach to trace points, Kprobe, uprobe, and USDT. So I'll explain them a little bit what all they are, because I guess some people would not know what Kprobes are or what trace points are. And I'll target the tracing use case, which I really like, which means that we'll have a facility to trace the kernel, to hook onto any function, and look at what was the timestamp at that function, what were the arguments of that function, and we can get all this facility now with techniques like Kprobe, and for user space you can even do uprobe. So what eBPF allows us to do is to have those handlers for those probes run, which are now programmed, which means you can basically define your probes and basically define the handlers of the probes programmatically from user space using BPF expressions.
So I have a
So,
question.
yeah.
Um, it's coming from a security angle. I mean, eBPF basically is its own language that you're introducing in the kernel. It has its own. You compile it and you dynamically load
Yeah.
arbitrary arbitrary code into the kernel. So
Yeah.
what features exist in eBPF to ring fence potential problems in your eBPF?
Okay. Okay, so there are a lot of restrictions. So don't so this VM, don't think of it like a Java VM running inside the kernel. So this is a very limited VM which has a lot of safeguards already there. For example, you cannot have more than 4096 instructions. So a program will be pretty small and it'll be pretty fast when it executes. So you can also so the verifier also checks that so all the paths taken from the start, they terminate to the end of the program, and it's just like one single function block. You cannot have loops inside the program, and that also the verifier checks. I guess you can have forward jumps, you cannot have back jumps, so you will not have the graphs which are going where the edges are going back. So basically there are a lot of these checks. There are functions which are supposed to be executed from inside those programs, and then there's only a limited set of those functions which are called as BPF helper functions. So the helper functions are the only set of functions defined inside the kernel which are allowed to be called from inside BPF, which means that if you have a BPF program, you cannot just call any arbitrary function. Even if you have to do like print k, then you have to do BPF trace print k. So it's not going to be like any generic function you'll call and it will get executed. So that's also a basic difference between having a BPF program run in your kernel or writing your own kernel module and then have the flexibility to execute any other function inside the kernel. And then yeah, there are a lot of checks which are there in the verifier, and verifier is pretty strong, and it's also a very in-depth piece of code. We can give get a like small glimpse of it when we look at the code.
Sure.
Does that answer?
Yeah.
Okay. So so BPF, because now that's what I call by stateful. So because it allows in-kernel trace aggregation, which means that because you control the handlers now and you provide the handlers from user space, you can basically put some states in your programs, look at the values, and then say that, okay, if the PID is this, then only I'm going to trace it. This also means that you can do filtering. There is another thing which is called as BPF maps. These are certain data structures inside the kernel which are accessible from BPF. There are hash maps, there are arrays, and there are like a whole lot of these maps. And what you can do is from your programs, store values in the maps and access values in the maps, do lookups and update the elements and do like basically the way maps work. So you can do these maps and you can access these maps from user space. Uh, Direct calls via BPF syscall. So there's a dedicated syscall now, which has been there since version 3.18. And with this syscall, you provide certain arguments to the syscall, and you're able to operate on maps. You're able to operate on the program. You're able to load the program. You're able to update the BPF program. You're able to update the maps, delete elements from the map, or basically do a lot of stuff. We are going to see that. So now the last question about extended BPF which you would have is like, we are always talking about inserting some kind of bytecode in the kernel. So what is that bytecode? So basically that bytecode is generated now using LLVM clang. So LLVM clang now has a subset now, which is like a machine, a target. and the target is BPF. So if you use that target, basically LLVM will generate an ELF for the BPF machine, and we'll see how it's used. So a program for BPF would look something like this. You'll write a program in a restricted C syntax, because it's LLVM Clang, so it expects like a certain C kind of syntax. And then you use LLVM Clang directly or through its APIs, and you use it to generate your BPF bytecode. The bytecode gets inserted using the BPF syscall in the kernel, and then there is this verifier plus JIT pass, which checks if the bytecode is fine. We can execute it. It's only calling the functions which it's supposed to call. Then it just in time compiles it so that you get more performance, because now it's not going to interpret the bytecode in the eBPF VM, but basically it just outputs the native code. I guess this JIT is supported for most of the important architectures. There is for ARM, there is for x86, it's for S360 also, and I don't know, there are some other architectures. I guess PowerPC also. I'm not sure. We'll check that out. And this JIT is able to compile it to native code, which means that basically now your program which you defined in the user space would look exactly like a small function inside the kernel, which is in your native code. And this kernel can then be hooked onto certain kernel functions. So these kernel functions, as I told you, would either be uh, like network filtering points inside the kernel. If you look at CLS, and if you look at Kprobes, if you look at static trace points, you can hook onto these kernel functions. And then when those kernel functions are executed, your BPF program will get executed at that point, which is going to decide what to do next. So it can update some maps. And if it updates some values in the maps, you can have a reader which just reads from those maps and looks at those values. You can also do things like from the map directly, like trace print k. So this is like an overview of how this program would work, how a BPF program would work, what it does inside the kernel. Now we look at a little bit more in depth with one use case, which is tracing. How we use EB. Yeah.
So before we go ahead, Amit had a question. Why is there a GCC backend also for the BPF? And to add to that, I wanted to know what the front end for the BPF program is. Is it regular C or is it something else?
It looks like regular C, but it's a bit restrictive in the sense that I mean, you cannot call more functions or you cannot do, but basically it's exactly like looks like C. I mean, the syntax is C. We look at the syntax as well.
Okay. So
yeah, okay.
basically
Do you want to? Yeah. Okay. I'll just show you some code. So for example, we have trace underscore read.c. So this is your BPF program. And okay, so it's basically C. Okay, and there are certain functions which we'll see here, and there are certain macros like sec which defines these functions are going to these sections inside the ELF.
Okay.
And when you compile them, they get compiled to like this. Okay, which is basically BPF ELF. I don't think we can see that, but there is LLVM obj dump. I had to compile it separately. And if you look at that, okay, that's the dummy. If you look at like read, so it spews out the BPF bytecode.
So
okay.
So is there a GCC backend for it as well, or?
I remember there was some work being done. I have no clue right now where that's gone, but this has basically become a standard. So there may be a GCC backend, and it would be really fun to have that. But I don't know what the reason was why that was not pursued further, and they pursued the upstreaming it to Clang and LLVM. Probably it was easy to do that. And at the same time, LLVM Clang provides APIs directly so that you can have them inside your programs. So you don't have to run Clang separately. So you would just like call those APIs like MCJIT and like other APIs which are able to compile the BPF programs to like LLVM's IR, then IR to BPF bytecode. So basically, they have those hooks directly, so you would not need separate running the Clang separately.
So is there a spec somewhere for the BPF bytecode?
Yes, there is a detailed spec, and there was some efforts done. Okay, let's just check. Okay, I mean, we are here only, so we can probably check. Uh, there was something. Look, but it's in obsolete now.
And it's on GitHub.
Yeah.
Somebody just forked the repo and probably tried to add some.
Yeah. So yeah, okay. Oh, look, it's Alexi who did that, like January 7th. Yeah, so as I said that there was some work being done uh, at that time with the GCC backend, but I don't know. Now everything is Clang. So should I go ahead?
Yeah. Thanks.
Yeah. So we target the use case for tracing now, and the tracing use case, we basically look at Kprobes and Kprobes. So for those of you who don't know what tracing is, it's a mechanism where you don't have to basically stop the process, but provide certain hooks to the functions, and the program just runs very normally. And in a very low overhead manner, you're able to get some data out from your programs. So how you do that usually is that uh, you have a method, and you hook onto the method entry or method exit, or you can hook in between somewhere, and then you run a small handler which handles whatever is being which handles and reads data from the kprobe or from whatever the function you wanted to trace. So this way what you can do is you can have an infrastructure ready, and actually kernel has that infrastructure ready, where there are either some static trace points which are already put in the code, or you can dynamically insert yourself in any kernel functions, any by mean like any allowed kernel function, and you can investigate its data. So this facility allows us to get timestamps at the entries exit, get timestamps at whatever place you hooked onto, and allows us to identify performance bottlenecks happening inside the system. So this is basically what tracing is in kernel's context. It can also be used in user space context. So you can have like your own small function, and that function you can just put it. Basically, it's like putting logs, but it's faster than putting logs. So that's what it is. So even a small printf, you can define even a small printf anywhere in your code. You can say, yeah, okay, I'm tracing the code. So wherever you put in your function. So, but these are more elegant mechanisms which allow you to control the tracing. So tracing is not just instrumenting the code, but it also means that you are controlling what is coming out from the code. So Kprobe allows us to do certain kind of tracing mechanism. So what it does is that you may have uh, okay, so you can go on this. So you can go in the kernel documentation and look at Kprobes, or you can go at this documentation on kernel.org, which tells how to use Kprobes. Okay, this is something about the documentation. So, but before that, okay, let me just explain. I don't know if it may take a lot of time. Okay, so but I don't want to let this go because this is important, and what we would do with BPF would be like the base of this. So what we do with Kprobes is that we decide a certain kernel function. For example, we want to investigate what's happening in that kernel function. So what we do is so for example, this is do sys open. Okay, bad handwriting, sorry. So what we do is we register a kprobe, and we say that, okay, we have a handler function with us, and this is a handler. You can do this in a kernel module as well. Okay. So what you can do is, or there are already defined events which are there in the system, which are trace events, which actually kernel developers have very uh, like sat down and thought about and said, okay, these functions are of interest to us, and we want to know what happens in these functions, and we want a mechanism which can say which allows us to express very easily what we want to probe, and when we just probe that, it's going to execute a certain handler, and which is going to give us a certain event. So collection of known trace points in the kernel or known important points in the kernel are called as events. Okay, and we'll see what those trace events are. So for example, we have do sys open, so and we want to put a probe. So what kprobe allows us to do is replace this first instruction, which of the function, and put a jump there. Okay, and this jump then goes on to Kprobe's own mechanism of inserting a handler there. So it's, I guess, like pre-handler or something, and that basically calls your handler, which you have defined. So at this handler, and with that, it passes you uh, all the context. For example, for an entry of a function, it can pass you all the arguments, okay, of the given function, and those arguments basically just go to your handler, and you can decide what to do with that. So you can say, okay, save them to a file or save them to a buffer, okay, and then you can read from that buffer later on. And once your handler gets executed, it then returns back to the last instruction through obviously special hoops which are happening. We won't go through that, it's too complex. So and then your function starts executing normally. You can put these kind of kprobes at the end of the function as well. So at the return time, you again have like your certain handlers, and those handlers will be like return probes. Okay, and when those handlers are called, you will see, okay, this all happened inside the kernel, the return code was this, which means that your function was completely executed. So for a tracing scenario, if you decide in your handler to put a timestamp here, so you get like the timestamp here. Okay, so it's like tick tock. So you have like a timestamp here, and then you have an probe which is at the entry of a function and then at the exit of a function. So what you will have is two timestamps, and what you can do then is to find the delta t, which is the time of this function, which means that tracing would allow you to in a very granular fashion, give you a very detailed time of what happened inside a given function in the kernel. So this allows us to identify very important bottlenecks. For example, scheduling latency, interrupt latency happening inside the kernel. What happens when you press the key spacebar on your keyboard, okay, and something was slow? What happened during all those events? It's going to identify all the interrupts, what happened at that interrupt time, and then the next function, and then the next function, along with the deltas of all those functions. So you'll have a very, very granular insight. So if some function took more time than it usually takes, you can say that, okay, there's a problem here. Okay, so
So
this is the
what
kind
sort
of.
of what sort of operations are actually possible in your handler? I mean, is it mostly just data inspection and reporting, or can you do more complex stuff?
You can basically do very rudimentary stuff, data inspection and reporting only, as you have just said. So it would basically be, you know, uh, get the timestamps. So the functions in the kernel to get the timestamps. You can actually do a little bit more than that, but what happens is that change change the arguments. Okay, so when the probe returns, it's definitely going to replace all those arguments. So this is so basically you cannot change the flow of the um, function, but you can inspect what was happening. Okay, inspect the arguments, get timestamps and stuff like that. And in tracing, that's basically like what is what's the requirement. So these all mechanisms to use kprobes or to use so there are other places, for example, in other places in the kernel, so they'll have static trace points already defined. So these will, okay, I think I should go back to the code, it will be easier to understand that way. So talked about, okay, where are we? We are in Linux. So let's go to kernel, and let's go to, I guess, IRQ. We were talking about IRQ. So let's go to IRQ. And I don't know, there must be handle. So handle looks like there must be IRQ handles here. So handle. So there are certain trace points which must be there. Ah, okay, here we are. So there is trace underscore IRQ entry. Okay, handler entry. This is like handle IRQ event pursue view, and you'll find these functions inside the kernel a lot, which will start from trace underscore, and they will have like the name of an event, IRQ handler entry, IRQ handler exit, and this is just one place, but they will be everywhere. And these functions are, these are actually not functions, but these are macros, and they get expanded to a macro called as trace event macro. So which basically puts an which basically defines a static trace points inside the kernel. Okay, so this is a static technique to identify what was happening inside the kernel. And what we just discussed here was a dynamic technique where we decide that we want to identify only this function and we only instrument this function, and we are not instrumenting, we don't have statically defined trace points. So what you can do is there can be handle IRQ entry, or I forgot the names of the function. So yeah, okay. So for example, what we can do is we have handle IRQ event, and what we can do is put a Kprobe here. So usually there is no static response here already. Okay, but kernel developers have identified that it's better to put a static response inside this function, which is actually calling the IRQ entry, okay, which is actually calling the handle event per CPU. But what you can do is you can say, okay, I just want to put a, trace point here. So in that case, you will use a Kprobe. So basically, if I want to define it, I would say that this is a static tracing technique where you put trace IRQ handler entry. These are already defined trace points inside the kernel. And what we are doing with Kprobe is a dynamic tracing technique for the kernel, which allows us to provide an arbitrary handler. So these handlers are very specifically defined and they output data in very specific areas. But here you can define where I want my data to go, which means that Kprobes is a very nice technique to hook onto if we have something like eBPF, where and that's exactly what happens at Kprobe. And let's come back to this diagram. So what happens is that when you insert a Kprobe, you can, and you use BPF, then you can say that, okay, I want my probe to be actually, I want those handlers to actually call this BPF code instead of going through any other code. Okay, and that BPF code will then decide what to do. And that BPF code at the same, someone has a question?
Oh, since you stopped, I have a question.
Yeah.
So, is this entire process sequential? As in, you hit the probe point, then you call the handler, and then the handler returns? Or is it something like hit a probe point, notify some thread which calls the handler, and then continue execution?
Okay, I think it's sequential, but okay, this I'm not sure, but I'll have to look at the code like more further. But I think it's sequential. Yeah, it should happen in an interrupt context only.
Because if it's sequential, it actually seems like significant overhead. Right?
Yes. Kprobe, if you use this jump technique, it doesn't cost that much overhead. But if you use a technique where you want the probe to be put here, for example, so there it will actually put an interrupt int3, and then the int handler will take a lot of overhead. This basically is not that much overhead. We think that it's a lot of overhead if we use these optimized Kprobes where the jump is there, but it's not It's not a lot. Okay. And also it's dynamic. So you basically just probe the points which you are interested in. I mean, that's it. And it's the same for these static trace points. So even these are there, it doesn't mean that they're going to be called every time.
Yeah,
So when you enable tracing, then only these are going to be called.
yeah. So they're essentially in the node section, right, of the binary. They're not
Yeah.
actually, so they're not actually part of the function. They're essentially in a separate section in the elf. In the node section, I think it's called.
Uh,
So
I
that's
did.
only by as in only when you're tracing everything.
Yes, only when we are tracing.
Right, right. Okay, so in that sense, you're saying it's no overhead. Is it?
Yes, yes. In that sense, okay. If you enable a kprobe on all kernel functions, then it's not going to work. Also, I think there is a max limit for how many kprobes you can put. So like there are controls to not like bork the whole kernel.
So,
So
uh,
yeah.
some of these things you could already do this with things like system tap earlier.
Yes.
That uses Kprobes, right?
So yes, so System Tab has facility to basically what System Tab does is that it has some scripts, and those scripts get compiled to certain kernel modules .kos, and those modules basically use either static trace points or they use kprobes or whatever mechanism you want to have. So
Like,
System Tab basically
what
is like
has,
a wrapper around these base technologies.
yeah, so what has BPF, what has eBPF brought to the table that wasn't possible before?
Okay, so the idea of generating so system tab fails a lot. Okay, if I show you the graphs, then you will see that it's really horrible. So I mean, no offense to system tab developers. I mean, it was the pioneering work in a sense that it allowed the same amount of flexibility which no other uh, I mean infrastructure had provided at that time. I mean, which means that dynamically generating kernel code, compiling it to kernel modules, and then inserting those modules and having a mechanism to get the data out from them and show them, and have a script which is like amazing description of your tracing. Okay, what you want from your traces. So they had all of these technique, but the flaw in my opinion was that there were just too many moving parts at that point, and generating kernel objects directly and inserting probably was not like a good idea. There were other mechanisms in other operating systems, for example, dtrace. And dtrace had a more elegant approach if you want to consider dynamic tracing. And what BPF allows us at this point of the time is almost the same amount of functionality and even a little bit more than what dtrace could provide at the time. Because we don't want a mechanism where a module is there and it's generated dynamically and then inserted. Okay, we want a mechanism which is seamless, where there is a proper verification done and it's the bytecode is limited. It can only do certain important actions which are required at the time, and like not do anything. So I have run multiple benchmarks with system tab as well, and at some point of the time there was like 580 times the overhead of using a normal static trace point or using dynamic tracing. So this is really slow. And 588, I'm saying when you use like multi-core machines, like 64 cores or something like that. So there is definitely an overhead in system tap, and it would not always work. There were, if you knew some scripts, they would work very properly, and those scripts were able to give you what information you need. But on other systems, they will just simply not work. I mean, I tested it with 4 systems, and like 2 out of them, the scripts which I was writing did not at all work. They would just break, and you'll have like kernel panic or something. Okay, should I go ahead?
Yeah.
Yeah. So now we are able to put kprobes, and the BPF code is going to be run with those kprobes. We look at the source code and that how this is happening, and then what can happen is that this BPF code can output data to certain mechanisms which are already there in the kernel. There is this perf infrastructure, which has its own perf buffers, where you create perf events, and those events go into this buffer. And then you have a user space part, which uses BPF syscalls, or which directly reads from these buffers and the trace files. All the data can go onto maps. These maps are maintained inside the BPF program, and they are accessible from inside the program as well as from the user space via BPF syscalls. So this way you can provide some state to your program, and at the same time you can provide a mechanism to output whatever trace data it is generating. So this is so with BPF and Kprobe, you're able to do like a small tracer of your own, I would say. So it's like an infrastructure to build more complex tracing techniques. So let's do a small demo. And this is actually the demo which we were talking about, and I was trying to show you. So what we do here is, let's go to the make file and I'll show you what's happening. It's basically just running clang uh, with emit LLVM, which generates like the LLVM bytecode there, and then we pass it to through the LLC, which is I think low level compiler of LLVM, which finally generates the ELF, which is containing the BPF bytecode. Okay, so basically it takes in a C restricted C file, which we just saw at that time. Let's look at a simpler one, and probably it's going to give us some more insight. So here is a small BPF program, and we define a section called as Kprobes sysread. I'll explain to you why we need these sections. Okay, this is how BPF is running these days. You have like two sections of the code. One is the BPF program, which is compiled for the kernel. It goes inside the kernel, and then there is a user space part, which is like which you can have in any language. Here I have in Go. You can have in Python. You can have in C itself. So if we go in like for example, samples BPF, you can see a lot of these programs already there, which have like a kernel part, okay, like user part, and then there's a kernel part. So kernel part gets compiled to the BPF bytecode, which is this inside this ELF, and the user part, which basically loads this kernel part and finds out where the bytecode is, uses the BPF syscall and inserts the bytecode in the kernel. So we'll have a quick run through of that. So here, what happens in this trace dummy thing is that we have a small function which we call kprobes sysread, and this function gets compiled to BPF bytecode, and this BPF bytecode gets and it just emits all of this and makes an ELF out of it. So if I've already done this make, so it generates this trace dummy.bpf, which we just saw with LVM objdump, I guess, trace underscore dummy.bpf. So you can see that we had like a section kprobes sysread, and it just has 3 instructions right now because the other ones are commented. So I'll explain to you why they're commented. I mean, we'll actually enable them and see what's going on. So here it does a call for 14. So we saw this here that there is a call being made here, and this call is what I was talking to you about, some restricted functions. So only these functions are allowed to be run from inside BPF, like get current PID, BPF trace print K, and there are a lot of other functions we'll see in the slides later on, but just to identify what these are. And these are already defined, and like when you disassemble your code, so LVM tells you that this is like function number 14 out of whatever that table was. Okay, and then the R0 value is 0 here, so the context goes in this register. So there are R0 to R10 registers, and this is the context which you pass to a BPF program. So there's always an initial context which is passed to a BPF program, and goes in R0 or R1, I forgot. Okay, and then it says, okay, set R0 to 0, and then just simply exit. So what happens is that we can load this BPF program and we can insert it. But let's do something more interesting here. Now let's make our BPF program a bit more complex. So what we do here is now we get a PID, which BPF program can get by running this BPF get current PID TGID. So if you want to see what's happening here, okay, no, let's look at here only. We'll come back to it later. So what happens is that we have BPF PID current PID TGID. What it does is that it looks at the current pointer, which is a task struct of the current process on the CPU, and it finds its PID and it puts that PID here. Okay, so we have the PID of the current process from inside the BPF program which was running. So then what we can do is we can then use some helpers in BPF. I think they are just macros. And what was that? Hold on. Regs param1. So yeah. Okay, so basically it just looks at the so this small macro, what it does, it just looks at the DI, SI, DX, CX, and these registers. Basically, it's just calling convention. So yeah, oh, hold on, yeah. So basically, it's just calling convention. So the context for this kind of program is ptregs, which means that if we look at the DI, SI, and all those registers, then the DI would have the first parameter to this function. And this probe is on a sysread. So it basically would be the first parameter of sysread. And what's that? I think it's number of bytes or file descriptor or something like that. No. Yeah, it's file descriptor. And then there's a buffer pointer and the number of bytes. Okay. So we get, so what we do is we get the file descriptor. Oh yeah, I already wrote it here. So, and then the third parameter we know is the size. So we take this size and we take this file descriptor and store it. So this is all being stored inside the BPF program for now. Okay. Then we can do some basic filtering. So we can say, okay, if the PID is not 12095, so basically actually it stores in the lower bits the parent PID, PPID, which in kernel context would be the thread group ID, isn't it? Yeah. So basically we look at the PID of the process by doing this, and if the PID is not matching this, then you just return. If the PID is not matching this, yeah, then you just return. Okay. Otherwise, yeah, let's go ahead. And what it does is that yeah. So now what we do is that we use another function called as BPF trace print k. So what this function does is that it's like a print k, but it's a special print k. So this is also another restriction in BPF. You cannot provide like strings directly here. You have to basically format the strings properly. You have to run a print k, which requires the size of parameter of the print k as well. And these format specifiers are also different for BPF. So, I mean, there are only some allowed specifiers. You cannot go beyond that. So what happens with trace print k is that it takes all of this data which we just collected inside the BPF program, which was run at every sys read happening in the kernel, and we just pass it to the trace print k. And trace print k is a special print k which prints on a trace pipe. So here in the presentation, we saw here that this trace pipe. So you can send these events to a trace pipe, and those trace pipe then sends those, you can then read those events from user space. Okay, this is too complex, so let's take an example. So Kprobes, as I was telling you, can also be set from user space. So I had set one somewhere here. So the Kprobe infrastructure is exposed in this directory in the debug.fs. So it says kernel debug tracing events Kprobes, and currently there are no Kprobes. Okay, but you can set your Kprobe. So for example, I did this. Okay. And okay, let's. So I'm trying to put a Kprobe here. So here there is no eBPF involved right now. Okay, this is just raw Kprobes being sent from the user space, and we'll see what happens at that point. So we have, for example, it was FD, and we put it in this. Okay, so the Kprobe is there, and then we enable our Kprobe. Okay, and now if we look at that special file, which is a trace pipe, look at the special file, we'll see some data being output there, and this data will come out from the kernel. So kernel is deciding this output. Sys kernel debug tracing trace pipe. So at every sysopen that is happening inside my system, I'm having my own event which is collecting the file descriptor, and it's also giving me the timestamp, and it's also giving me which process is actually opening that. Okay, so let's disable it. So this was an example of how we were using Kprobe. So if we come back to this diagram, so by doing this, what we just did was that tell the kernel that, okay, put a trace probe at the entry of the function, give that probe a name called Bololo or whatever, okay, and put that in do sysopen, okay, and at that time collect fd this. And how do we know that it's supposed to collect like fdax is because we define this format that, okay, so it's going to collect ax, and there will be it should contain fd. Okay. Oh, that's yeah. And then we put it to the Kprobe events. So what happens at that time is there is
Uh,
yeah
One question.
yeah
Can you read a little bit more on the FD equals AX? Uh,
what
can you elaborate a bit more on the FD equals percentage AX? As an
uh,
example, you get FD from what percentage AX means and so on.
okay. So what happens is that there are certain, so we know that for a sysopen, what would happen? Okay, so kernel has defined already some events inside the system. So sys kernel debug. Oh, I need to be root. Let's go back to this. Okay, so uh, Kprobes. Okay, events. Oops. Hmm. Mhm. Okay, let's go back to the documentation. So we have these event formats.
Can you zoom in a bit?
Okay, and the DFD will be the AX register, this will be the DX, and this will be the CX. Okay, and we put these formats, and once we put them, and then we get the format. Yeah, I was supposed to show you this format. So this is our event format. So where am I? Kprobes, events, Kprobes. Okay, okay. Okay, so when we define the format, what we do is that we say that what the probe is going to print. So which we just saw when we saw the trace print k, and here we tell that the format is going to be the format is going to look like this. So there will be fields. This is common fields which are there, and we define the first field, which is the probe IP, and we define that it should be AX, and it should be formatted in this style. Okay, that's what it is. Okay, so when we enable those Kprobes, it's able to collect from those specific registers and give the values there. And basically, that's what we are. So what we did here and define it in our own string way or whatever it is, we can just do exactly the same here with BPF. And this handler will be called when Kprobe is being executed. We'll go back to how that thing is exactly happening. But when this handler is called, we basically decide that we are going to collect all of these things, and we'll collect these parameters, and then we are going to trace them out on the print them out on the trace pipe. We can do something else also, but this is an example of printing on the trace pipes. Yeah. So when this runs, so let's just compile this. This gets compiled. Then I think we need to build this. I'll show you what trace_dummy.go does now. Okay. So if we see trace_dummy.go, yeah. So what it does is that it uses. Okay, I don't know if I should go in depth and explain all of this, but I think this is enough. And so what it does is it creates a new module out of this. So it parses this BPF file, which is the ELF file. It looks at all the Kprobe sections inside that file, and first it loads it goes through all the ELF sections. It fetches whatever BPF instructions are there, and then it does a BPF prog load. So I've gone through actually this code already. So it goes through BPF prog load, and this BPF prog load is going to call the BPF syscall, which with the whole BPF instructions, and just load the program inside the kernel. Then it goes over all the Kprobes, which it identifies by going through the section. So it identifies that, okay, if this looks like, if the section looks like Kprobes and whatever sys_read. Okay, if it looks like that, then enable those Kprobes. Okay, all of those probes, and the probes are inserted. So when those probes are inserted, then the kernel starts associating them with then the kernel starts associating the handlers with these BPF traces, which BPF programs which we are going to run, and this is going to be executed at each of the probe head. Yeah. So let's just try to run that and see what happens. So okay, so it's looking at the trace pipes, whatever is going on inside the trace pipes, and it's printing, exactly what we were doing, but this time it's our program. Yeah. This is weird. Actually, it's not running. So our probe is not running actually. I have to see why it's not running. Oh. Okay. Okay, I know why it's not running. So what happened was that kernel has already defined some probes which are there. So when this BPF created a probe, it created the probe sysread already. So we can see it here. So if we do psysread, and we do its format, we can see that this is the format, and this is very weird. So okay, so this demo has been bogged. Okay, so basically what's supposed to happen, I'll explain to you, is so what's supposed to happen, I'll explain to you, is that it uses the kernel's own events which are already defined, and which I think I have disabled all of them, and I don't know why. So if we see this calls thesis enter. Okay, these are static. Okay, no, don't worry about them. Okay. Hmm. Okay, so actually I have booked the demo. uh, so what is supposed to happen at this time? I'll just explain to you just like that. Is that it's supposed to insert the probe. The probe gets inserted, and it's supposed to start the tracing and start reading the trace pipe at the same time and looking at the channel and printing whatever is coming at the trace pipe. Okay, but we are not able to insert this. The probe gets inserted, but we are not able to see anything on the trace, and that is very weird. So probably we did something wrong with the trace dummy.c. Yes, and what we did wrong was we have a filter. Okay, so and this filter I just specified. So let's do something. Let's start gedit. Okay, and let's look at the PID of gedit. Then it will be good. So basically, actually, what's happening is that the PPF Kprobe has been inserted and it's running, but we don't see anything because we have a filter set on it. Okay, so and this is something remnant from the past. So what we'll do is we'll do PID of gedit just to see that it's 16036 now. Okay, and then we'll save it, and then we'll make it, and then we run it. Okay, so the probe is still running, but what should happen is that every time I'm supposed to like type in gedit, it's going to write it down. Why? Because we have a probe on the read. Okay, there is a read going internally also, even when your program is just running, and at each and every read, it's going to go to the BPF program and it's going to print out what we decided to print. It will print hello reserve bit, FD, it'll give the PID and how much it reads. So it's reading 16 bytes. So this is something interesting. I mean, even at every keystroke I do in gedit, it makes a read syscall of 16 bytes. Okay, so we got this weird information today. It sometimes reads something more also. Look, I mean, what it's reading. Like even if we move this around, yeah, it's kind of fun. Okay, anyways, so we get the picture what's going on, isn't it?
Yeah.
So did people follow what went on, or should I need to explain a little bit again? We put a Kprobe on do sysread, and with what?
So you can ask questions. You want this better?
I'm listening to the questions if people have questions.
Okay, shy. Ask.
Okay, should I go ahead?
I guess.
Should I go ahead?
Sure. Yeah.
Yeah. So yeah, so basically what we did was we put a probe here and we gave it a PID, and we told we found its PID, and we said if the PID is not the gedit's PID, then just return 0, don't run the probe. So even the Kprobe was there, it was inserted, it was running it, but it was just returning empty. Okay, and so basically it was a filter that was like ruining the demo. Yeah, we should remember not to do this. So similarly, now let's look at a little bit more complex probe. We'll see. So this is a Kprobe at sysread, and so exactly like the way before, but here we introduce a little bit more function. So we do BPF probe read, which is able to read. So this read program can arbitrarily read from whatever kernel structures you provide and save them somewhere. So what we do is we just read it, save it to the ptregs args, and we have a map. So this is the concept of maps which comes here. So we have a map here, which is our read args map. Okay, and this read args map is containing our its read as maps key is U64 and its value is the ptrex. So what we do is at every time with PID as its key, which we get from here, we save the args, okay, and we update this in kernel map. And what we can do is at the return of the probe, which means that we push it at the top, update the map, BPF map here at the top, and then when we return, we check, we look up the map, and we get those args which were at that specific syscall. And then when those, we look at those args, and then we read something more. So we can do BPF probe read again, this function, but this time on the buff. So we can actually read the whole buffer, which is the second parameter of the read. So we can actually see what the buffer was having. And then we can put it to another helper function, which you can run from inside BPF, which is BPF perf event output. So this outputs your data into this perf buffer. So we saw the trace pipe demo, and this is the perf buffer. It outputs the data to the perf buffer, which is a per CPU buffer, and it's pretty nice. So you can actually, and you have ways to access it from user space, which are more elegant than using the trace read. Not probe read, the trace print k. And then we are able to, make a more comprehensive tracer rather than just use trace print k. So yeah, so I guess that's what this Kprobe and Kprobe does. This also means this is like a small example of using maps to maintain kind of states in the program, which means that you can update the maps at certain probes, and then in other probes which are inserted, which would be inserted at other sections in the kernel, you can query those maps and see if that was the case. So basically, this would allow you to follow connections if you do a connect. So and you'll be able to follow it through the kernel, and you'll be able to maintain that. Okay, if this connection was this, and then so similarly for like file open. So if you have a FD, so you can say that, yeah, for this specific file which was opened, how many reads did happen. So you can basically kind of maintain states in your programs. There are other BPF helper functions which are also there. Yeah, some question?
Is it fair to say that the maps are basically your local data storage within the eBPF framework, to store your own context as you're gathering all this trace data?
Yes, you can do that. You can create maps of complete events also. So you can put this. So this is like a hash map, which you can use it to maintain states, as I just told you. But these maps are also these maps can also be updated from the user space by syscalls. So these are not just internal. Obviously, they are internal kernel and specific to BPF. But because you can set them from the user space, you can look at their values from user space. This means that you can have like a better control of your program. So you can put like a, yeah.
So it's basically it allows you to. I mean, I'm just making a very crude analogy, but basically you're defining your own data structure in the BPF program, which is
Yes.
which is storing data that it is collecting whenever you trigger things, and over time you can query all that your own data and see whether it's a whatever histogram or whatever.
Yes, exactly. And that's one of the primary use cases of maps. We can do certain event aggregation inside the BPF programs itself at this time. So we can probably, for example, store for a given period of time all the size of the reads. So here we are able to read. So if we do param3, we'll get the size. So we can create a map which contains for a given PID the size of all the reads, and then we can present it after every second. Like from user space, just poll the map every second and just print out a histogram. So we can do.
If you go back to your slide, you said that you are actually shoving all this data into the perf buffers as well, right?
Yeah. So
So
so this
can you use the perf commands to get at this data as well?
yes, perf commands, not perf commands right now. So there is so it
So what's
makes
the
the
point?
events and puts it in the buffer, but you use the perf's APIs to read them.
Okay, so you couldn't use something like perf trace or perf whatever. You could.
Uh, I guess there is option to hook maps to perf events, but I don't know if the perf's user space part, which is inside tools perf in the kernel, that provides us an ability to read from the maps. I will have to check that out.
Yeah, I guess it's just a matter of linking it all up. Once you have the capability to insert that data, I think it's just
Yeah.
a matter of retooling it to actually use perf command.
Yes. So we did this small demo of Clang. So let's go ahead and go through.
Because then
Should
it
I go ahead? Yeah.
because then you wouldn't have to write your own programs to parse all this data, create histograms and all that sort of stuff. You could just use the perf infrastructure which can already do this stuff.
Yes, we can do that. But that's the thing, you know, the infrastructure surrounding BPF right now is increasingly becoming more powerful, which means that we have uh, so you can already see that so this example which I gave you with Go, it's using uh, so example which I gave you using Go is using this trace pipe. Okay, for now, which means the read the BPF trace print K. But if we use another technique which is there with this, it allows us to read directly from the perf maps. Okay, and provide even more and more detailed functionality. So I'll actually give you a small example what people are able to do. They can even generate very pretty graphs and all those nice stuffs directly from that. And for that, they don't need to go to the perf infrastructure and just run perf scripts. But yeah, that would also be interesting.
Actually, I would love to be able to use this with perf infrastructure because that's available with every kernel. It doesn't require me to write custom stuff because it's I already know the perf tools.
Okay, let's see if this allows us to do something with BPF right now. Okay, there's nothing
I mean,
here.
that's just a matter of time. Someone will come up with
Yeah.
patches to add that support to perf.
Yeah. I guess it's a matter of tooling. Probably they have reached it already, and I'm not updated about whether we can directly use it from the perf's user space tool. Okay, because these events are special events. I mean, the BPF events are not like normal other perf events. They are special events, and those events contain, you know, like specific data. So I don't know if they would do it or not. I'm not sure. Okay, so I should probably look that up and then update you on that. Hmm. So we did the small demo. So these are some major BPF milestones which we had. So in 3.18, we had the BPF syscall, which made everyone's life easy by actually using the syscall. We had socket support and the BPF math support in 3.19. Then Kprobes and perf event support was added. This thing which we just saw in 4.4, and Kprobe support was in 4.1. In 4.6, we could get stack traces, and we had per CPU map support with that. So you can add the same at querying a single kernel function, you could actually get a limited amount of stack. I guess it was like 1 page worth of stack. So you can get that stack traces as well for that. In 4.7, you could attach to trace points. So if you remember, I just showed you the trace points in IRQ, static trace points in IRQ handler thing. So you can attach to those static trace points as well, and not just Kprobes. And the static trace points are more stable in the sense that because they are static and they have been tried and tested across the kernel functions, they are more stable. In 4.8, you have Express Data Path Core, and you have the ACT plugins for BPF, which allows us to actually filter the, so this is a networking use case. So it allows us to filter the packets at a very lower layer, just near the NIC. So the layer between the actually the packet forming inside the kernel and the driver sending you the data. So it's near the driver. We can filter those packets there itself. So it gives a huge throughput and a performance for packet filtering. In 4.9, you can profile and attach to perf events. So to normal perf events, which you have defined, you can attach BPF programs. And I don't know if you can read them or not at the same time, but I guess you should be able to. So this is new stuff, and I have not I've not tested the 4.9, the perf events use case till now. In 4.10, we have the C groups support, so you could attach programs to specific C groups and socket filters at this time. And in 4.11, you can put trace points for eBPF debugging itself. Yeah. There was some question? Okay. So yeah, so we saw these program types. There is program type Kprobe, there is program type tracepoint, and the perf. This is related to tracing. These are for C groups, and the new upcoming is for security, the landlock LSM. And these are the map types. We saw two types till now, like the hash map, which is there, and the perf event array. There are others which are prog array, where you will have BPF prog array. There are per CPU hash maps, the stack trace kind of map, which stores this stack trace. There's LRU hash and like all sorts of new data structures which have come up. Let's go through the kernel code a little bit. I guess this is time to look at things, how they look inside the kernel. So what I would say, because we were sticking to the Kprobe use case, I'll do some like digging here, but we should probably be okay, and I won't waste much time. So for example, we were looking at Kprobes. So Kprobes, and we looked at what Kprobes was doing. So there is a function inside the kernel, which so when we had set up a Kprobe here, something like this echo, was it P or something? Yeah. When we did something like this, so what happens inside the kernel is that a specific function is called, because we are setting these values to syskernel debug. So it's in the debug.fs, and this file is exposed in debug.fs inside the kernel, and it's kprobe events file. So there's a function inside the kernel in trace kprobe, I guess. So most of the tracing stuff inside the kernel is in trace. So this directory contains most of the tracing related things inside the kernel. So there is trace print key, which defines what to print on the trace pipe directly. There is trace syscalls, which handles special cases of tracing for syscalls. The trace events, which are kernel's trace events perf. There is this ring buffer, which stores the incoming trace events directly. So there is also trace Kprobes, which we'll see, and I guess that will be interesting. So kernel trace Kprobe. Okay. So there's this function called as create trace Kprobe, and this is actually called when we provide this. Where was I? Yeah, when we provide this. So when we try to enable a Kprobe, this is actually the kind of function that is called. And this is also called when we actually do it from the trace dummy.go. So this is all happening in user space. So when we do this, enable Kprobe, it basically goes through this and enables the Kprobe. Okay, so actually we should probably go through this code, user space code as well, just to tell you, yeah, this is really happening. So Uh, okay, this is Go BPF code, and this is the ELF section which we had imported, and inside this is module.go or something like that. Yeah. So this write Kprobe events is called from enable Kprobes, and what basically it was doing was writing your probe to the probe which it got from the after parsing the header. You know, like the header of the ELF, it got that string, and it then tries to format this probe exactly the way kernel requires it to be formatted, like this, and it formats it in that form and provides that, okay, there is a BPF program attached to it, which it does it in the previous section when we do the load of the program, and then it sends it to the debug So basically, that's all what this is doing. So what happens when this is done from the program is this function gets called create trace kprobe, and this create trace kprobe then parses this whole string which we had given, like, oh, it's a probe, it's a return probe, or we want to clear the probes. So it looks at all those strings, and then it finds the trace kprobe, and if the probe exists, because on syscalls there would be like probes existing. So if it probes exist, then it like finds the trace probe and registers the trace probe, and you can see that it does like some yeah. So it creates this structure, which is the Kprobes structure, which contains all the details about what event it is, at what address it should put the probe, and all that information about it. And this is then this allocate trace probe then also basically does like a big kzalloc inside the kernel, and it gives you like the space to put all the data about the handler and whatever. And yeah, and that basically then calls and when you have that handler running, then it basically, the probe is there, everything has been inserted, then it calls the kprobe dispatcher and some other functions, okay, which are, I don't know from where do they call it, I guess calls it something. Yeah, okay. So the handler of the Kprobe, it tells that it's going to be this Kprobe dispatcher, and the Kprobe dispatcher is going to be called when the probe is going to be hit. So this is for return probe. There is for entry also. So this would tell whether when this probe is going to be hit, and what happens at that time is that this dispatcher, when you have this BPF enabled with you, it can go in different ways how it's supposed to dispatch. When you have this BPF enabled with you, your stuff goes through this trace. I guess it was BPF something. bpftrace.c. So bpftrace.c contains all of these calls, and the most important call here is this first call, which is the trace call bpf, which invokes the bpf program. And this is basically called from the kprobe dispatcher through other functions which goes there. And this trace call bpf takes in that bpf prog which we gave, and I'll tell you how this comes. So this is the second part which I'm explaining to you about how this kprobe handler is actually calling. So what we saw here, how this program that we just compiled was called. Okay, so we are basically just going through that. So yeah. So we have like this trace called BPF, which runs this BPF prog run, and this BPF prog run is a macro which runs this BPF prog. So this BPF prog is the structure which contains all the BPF programs, instructions, and everything. Like it contains all these details. And then at that time, we run this BPF prog run, and which calls this. Uh, which calls our BPF program and executes the BPF program. And we then send this data out to whatever happens inside the BPF program. Like we send it out to the buffer, perf buffer, or we send it out to the trace event. And so what happens when, so we saw in this section of our call that what happens at the Kprobe when the probe is run, and then when the BPF program is encountered, how the BPF program is called during the handling time. Okay, but now let's see how this program is actually sent. And this is something which would be very interesting. So there's always, because BPF is a syscall, so we'll have a BPF manual page which explains that, okay, perform a command on an extended BPF program or map or program. So you provide these commands as the first argument, and you provide a BPF attribute. This attribute is a structure inside the kernel which contains everything about the BPF program, its instructions, and all these details, and the size of the program. And when you make this call, it goes. So this call is definitely being made when we have our if you see module.go, I think it should be there. Yeah. So okay. Sorry. So if we see this, there must be something related to load, no? Okay. So there must be related to. Yeah, there is BPF prog load, which is this, and this is this. So it calls, so this program, which we already saw, what our trace-dummy.go program was doing. It was basically calling this function, which is load function, if you remember correctly. And this load function was going through this whole ELF section of the BPF, and it was going through, okay, if this is a Kprobe, then it finds out what the name of the Kprobe is after that. And it says, okay, if it's a Kprobe, then put the program type as BPF type Kprobe. And then it says that, okay, the size of the instructions will be this. It looks at because it's going through the section header of the ELF. So it can find out the size of the instruction. And then it gives a call of BPF prog load with the program type, the instructions, and everything. And this BPF prog load is like because it's Go, so they have translated it from C. So it's like this call in C, which builds the attribute. So it builds the BPF attribute, and then it makes this syscall of nr-bpf bpf program.load with everything. So now we know that a syscall is being made, which is made by going through our program, which was this. Oh, where am I? Oh, okay. It's a big. Right. Trace demo. Yeah. So which was going through this trace dummy program, and we were able to identify that, yeah, okay, it makes some syscall. So what happens at that syscall time is all the magic going on in this directory. Okay. Kernel BPF. And inside this directory, we have this syscall.c, which handles this BPF syscall. And this is the BPF prog load, which is called. So actually, this is called from this syscall. So this is the BPF syscall, which looks at this incoming BPF program with commands, attributes, and everything. And then it gets all this data, including instructions and everything, and it sees what the kind of command was. So if it's a BPF prog load, then it executes this BPF prog load function, and so it loads this BPF prog load function, and this function then copies this license copy, because BPF programs, if they don't have the GPL license, they cannot access the GPL only functions which are there in the kernel. So they check this BPF license, they look at the instruction thing, and then it does the BPF prog alloc, which does this program allocation, and this is in the BPF core. So we are now in the core directory of BPF, which prepares the BPF program. It prepares the program FP. It prepares like all of the things for BPF, and then it looks at the instruction count, copy from user. It copies all the instructions which are there, and the BPF instruction which are there, and then it does run the BPF verifier. So BPF check runs the verifier. So if we go through this, you'll see we are in the verifier, and BPF checks then. So this is like a complex piece. So it does like a big verification of. So it's like actually a static analyzer for a BPF program. So this will take a complete session itself to understand the verifier. So then it does fix up BPF calls. It has to fix up some calls. For example, if we have instruction immediate as this BPF's internal program, if you remember from user space, we would say BPF map lookup LM. So it gets translated to actually this actual function. Then it has to offset. It has to take care of this BPF's offset from the BPF's call base. So it does this small instruction fix up, and here it selects the runtime. So here we decide if we can JIT compile the program or not. If we are able to JIT compile the program, then so the function which is going to be executed is actually BPF prog run. And this is this BPF prog run, which we had seen previously, which is the so when a BPF program is run, it is actually calling the function which is in the BPF prog itself. And this function, if we are able to JIT compile it, we are able to actually have native code for that, which completes this section of what we were discussing. Where is it? This. So verification and JIT pass, and then the native code compilation pass. So this is able to then JIT compile the whole BPF program, and then we have check for tail calls. Yeah, because the BPF program can make tail calls, but we have to check for its compatibility, which means that a call can make at the end of the BPF program, it can call another BPF program. So yeah. And then it creates the BPF prog new FD, a new FD for the BPF program. So this is basically like what happens when a BPF program is being loaded. So when it gets the instructions, and when it gets when the program is going to be executed, so we'll be interested to probably look at how it if the bytecode just directly goes there and it's not JIT compiled. Okay, so if the bytecode is not JIT compiled, then what would probably happen? So it will go through functions inside this, which is, I guess, yeah. So this looks like, yeah. So it runs the BPF prog run, which we had seen, which is part of the BPF prog itself. So if the program is direct instructions, then it runs this BPF prog run, which contains a switch case dispatcher for all the instructions. So it goes on instruction by instruction, and it identifies what instructions are there and then executes those instructions. Okay, and if the program is so this is how like all of the calls are supposed to be made inside the BPF programs, and they are going to run. So you can see if there is a BPF, if it's a call, then it does a call to the call base and the instruction immediate with the BPF register values which are there. So this is what we were seeing when we see this BPF call. So ll vgdum. So whenever we see like call here, call 6. So this is basically translated to the BPF call, which is like 85 instruction number or whatever, and that gets called to this allowed functions, and those allowed functions, I guess, are, I don't know, I forgot now. So probably they were in include. Uh, Sorry, Linux and include Linux. What was that? eBPF.h. Uh, yeah, yeah, yeah. So these are like your BPF helper functions, which are kind of the allowed functions from inside the programs. So let's get back.
So Chandra, how can you, so can you actually load multiple BPF programs, or how do you do that?
Uh, Load multiple
Okay.
BPF.
You
I don't
mentioned
get
it
it.
a different BPF program, right?
Yes,
So
yes.
for that, I assume you'll have to have multiple BPF programs.
Yes, yes. You can have multiple BPF programs, and then you can pass them using tail call. So so BPF has like its small file system. I guess it's in sys. Uh, let's go back to this root thing. Probably it will be better. Sys fs BPF. It has this small fs which is there. Okay, this I cannot open because I was doing something with related to work here. So it has a small fs where you can actually create the programs, and then you can store the programs. You can create a directory and your programs will be stored here. Or you can use a BPF tail call, which we saw. I guess it was somewhere here, no? Tail call. Uh, Yeah, then you can use BPF tail call and call the next program. So we can create like an array of BPF programs, and we can then call the next program from that. This allows us to like chain the BPF programs.
But you cannot do it like in the middle of a BPF.
Uh, I don't know. Probably you can. I don't know. No. You cannot. It's a tail call. So yeah, you cannot do that. You can do it like that. So you can have like a sequence of BPF programs which are executed after one. I don't know what was the use case. I completely forgot. And this is kind of new to me. I have just used it once before, so I don't know
I can,
much about how.
yeah, I can imagine it being useful in the sense that if you have, uh, let's say if you have something that collects only statistics of some function call, and now you want to write
Yeah.
a BPF program that say computes an average. So or
Yeah.
whatever.
Yeah.
Actually, instead of rewriting that BPF program, you modularize it, right? You write a separate.
Yes. That's possible. So you can have like a filter inside your all BPF programs which say that after some time call this tail call with this BPF program, something like that. Yeah, I don't know. I'm just thinking.
As in,
Okay. Anything? Yeah.
it is useful. As in, it's not okay.
Yes. That's definitely useful. I'm not exactly sure where they are using, but I guess they are using those tail calls related to with C groups or something. They're using in their like container stuff or something like that. So I'm not exactly sure where. Oh no. Okay, I remember. So those tail call things are being used for networking programs for XDP. Yeah, I think I remember that. I've seen them once there, but I think we can use it for normal tracing programs also. I don't think there's like a problem with that. So going further, so this was our BPF small interpreter, which is running inside this kernel, and we provide it all these instructions. There are these classes of instruction, and the way it reads all those instructions, and then how it computes them. Or if it's a JIT compiled program, which we saw, I'm sorry, caps. So which we saw we got from where were we? eBPF prog load. So here there was this. Yeah. So here there was this thing, eBPF prog select runtime, where we would try to JIT compile the program if the architecture supports it. And sometimes, okay, so we can see here, it's for x86, S390, PowerPC, and ARM. So for example, we can go for 4 and we can say how for x86 BPF will JIT compile this. And it's pretty interesting. So it will just do like an interpreter, and with every instruction that it sees, it does this with every instruction, it does this do JIT thing, and it looks at all the instructions, incoming instructions, and translate them to x86 calls. So for example, this is like move x, and it makes it like 0x89. So like there would be call or something. So you can see it emits push RDI pop. So you can see like it builds like this calling convention style. So, and then the whole BVF program is built as a single function, as I said. So there's always at the start of that like a preamble, which builds like basic. I don't know where it is. I think it's been here prologue, which builds like the function prologue. So this is for all BPF programs, and it looks like how functions are. I mean, see. 55, 48. So it builds this BPF program as like a single function unit, and then when we and then when it gets executed, so it selects the prog as either the so in the prog it selects either the runtime, which is supposed to be an interpreted code, or it's still supposed to be a native code. So is there anything else that is interesting in the source code? There is verifier, which is interesting, but it's I don't know. I mean, I'm scared of it. I'm supposed to understand it, but I don't understand it completely. So yeah, I think it is this like check BPF check. Here the verifier starts, and okay, it's an initialization stuff. So probably did something here. What? Okay, anyways, I mean, it's going to take a lot of time to understand like how the whole verifier works. It does like a like in short, I can explain like what it's doing. It goes through all the it creates like a small CFG of the program, goes through all the branches and sees if they terminate to the return, which is for the function, and if the whole program is made as a complete function. It sees if the jumps are not outside of the boundaries of the program and things like that. So, which brings us to front ends. And we saw a small demo of writing our own programs with C and compiling them ourselves. And you know, like, by the way, I didn't show you something which I found out today morning. And basically, if you do strace space dummy, so you see this BPF program being called, and you can actually see like, hey, look, it opens this, it opens its PR reads the whole file, which is your whole BPF file. It gets all the strings which are there, and like it reads all of them, and then it makes this BPF syscall with program load and with the type. So it identified here that the type was probe, Kprobe. It looks at, okay, there are 35 instructions in the whole program, and then instructions, and then the license and everything. And so basically, yeah, it was fun. I just found out like you can do that today. So yeah. So now we come. So till now, what we were doing was that we would compile our own program, use Clang to compile it, and then convert it to this and this. So what we can do is there are these new things called as BCC, which is a BPF compiler collection. It's a new project. So from IOVisor. So yeah. So this BPF compiler collection project, what it does is that it allows you to it gives a big infrastructure and a toolkit for creating efficient tracing and creating BPF programs, inserting them, and getting their values out. So there are a lot of examples you can already see, and there are tools which are already created. There are people like Brandon Gregg who are doing it for tracing and hey, look, a small example I did. So there are Shasha Goldstein, and he did a lot of work on user space tracing. And Brandon Blanco, he is maintaining all the backend parts and everything. So they did these lot of efforts to actually make a set of tools with BPF to analyze the whole system. So and this is pretty nice. Can I do this? Yeah. So this is pretty nice. So we have all these BPF tools now, which are basically small scripts. And those scripts, when you run them, they are able to provide you, they are able to insert these small BPF programs, fetch those values and make analysis and, like find out what's happening in your system at different layers of the system. So it's able to do all of that. And this is pretty interesting, which I see. And how it does is that it has this backend. It has this front ends in Python, C, Lua, Go. We use Go BPF today, so which we just saw. There is Python, which is the most important one, the front end there, and it compiles the BPF programs directly via the LLVM's interface. So we don't have to run Clang separately from that. And then it also has functions to load them directly in the kernel, and then also manage its maps, the BPF's buffers, and all the probes which you have just inserted. So this makes BCC like a big framework with which you can quickly build small tracing tools. So for example, this is a complete BPF program. I'll come back to the slide later. Don't see that. So which gives you a complete BPF program. So I have a small example here. For example, if you see trace fields, it uses a Python module because this IOVisor gets compiled, and by default you get a Python module, but you get all the bindings with Go, Lua, and everything. So, but now here we use Python. So you can just do from BCC import BPF, and you actually give your whole program as like just a string. And when you run this, when you initiate this BPF program, BPF object, it basically compiles it and gives you the BPF object. And you have these small helper functions, just like we had in Go, to attach to the Kprobe. And you can specify, okay, attach this to sysclone. And when the sysclone is attached, run this function hello, which is the BPF program, and print this PID message from this pipe which is in the trace print. So when you attach to Kprobe, there is a BPF trace print key happening inside it, and that BPF trace print key is printing to the trace pipe. So this allows us to print the data out from the trace pipe. So this is a complete tracer for a sysclone, from where in user space you had defined what I'm supposed to do at this sysclone happening. So this is pretty powerful. So if you do like this, so at every sysclone that's supposed to happen is going to print me its PID, what was the clone process, and whatever message that I had printed. So you can create these small tracing programs, or you can create more elaborate tracing programs. And indeed, they're like really very in-depth tracing programs that have already been created. And you can just look at this directory, tools directory, which contains all of these tracing programs. For example, block IO latency, okay, bash readline, this is user space. So CPU distribution, you have IO snoop. You even have a complete tracer here. So there is like a trace Python script. Where is it? Yes, where is it? Yeah, trace. So there's a trace Python script where you can actually just tell that trace sysexecve the first argument and print it as a string. And if you do that, it's just, you can see the screen now. Should I increase the size? Yeah. Shit, it's so slow. Hold on. It's so slow. Oh man. Okay. So you can see, like, if you do like sysexecve and this, you are able to insert a BPF program at sysexecve, which looks at the first arguments, prints its value, and prints it for you in such a nice fashion. So you can create these small tracing tools. You can create filters inside these tracing tools where the argument 3 should be greater than 2000. So all sys reads where the third argument was greater than 2000, like the size of the read. So if it was greater than this many bytes, it's going to print them. So this allows you, and this is just a single Python script. Obviously, it's like a big Python script. I mean, if you like see, where is it now again? Hey, there was a shortcut in GitHub to, like, you know, see the files what we want, isn't it?
It was T, I guess. Press T.
T?
Press the letter T.
Yeah, I'm pressing it, but nothing happens. Oh, so tools trace.py. So this is like, it's a big mammoth Python file which contains chunk of like C code, which is actually like built on the fly and inserted, like this. It replaces all of that and like builds you a BPF program. Like it looks very sketchy, but it works. I mean, it's been tested and it completely works. There are other tools like Connect, or like IO latency or stuff like that. TCP Life. This was really interesting. TCP Life. So it can summarizes the TCP sessions that open and close while you're tracing. So, and you can identify all of this data just by using BPF. So this was the Kprobes tracing example. So what happens inside the BPF compiler collection is that there is so you have this BPF C program, and then there's this Python module which we just saw here, which you, when you import it, and that Python module exposes the BPF. So this Python module then calls in the lower level BCC library, which is like libbcc.so, which is written in C++, and it gets compiled and exposes all the functions which you can use to build the program. So in that library, basically you have this BPF module in it. You initialize the BPF module, and it uses this Clang rewriter to rewrite certain instructions as BPF requires them to be done. And it generates the IR, and then you optimize the IR, and then this optimized IR is then generate the bytecode using LLVM MCJIT, and this bytecode then gets compiled using the load. So this whole library provides, it's like a primary interface, and you can see in libbcc.py if you want to see its implementation. So like if you're here, So all of the important code which is there in the library is in this, and in Python there is this all the implementation, all the functions which it can access from libdcc.so, and you can see that you can do module create, module build, you can function start size table, management of the table, look up elements. So it will give you all the APIs to actually build the complete function, and all the other heavy duty work which is done for building the program is done in this, in bpf.c and bpf module.cc, where you have all these functions which are like LLVMs exposed by the LLVMs rewriter, and which are exposed by so for example, when you create the bpf module here first, it initializes the target, it initializes the target structure, initializes the mcjet, which is the last stage. So there are multiple passes happening here of Clang, which then generate your bytecode, which gives you the final bytecode generated. And then the same library also exposes you all these facilities to load your programs. So here you can just directly see, you can go here and you can see that open perf buffer, okay, attach or detach to uprobes, attach or detach to kprobes. It provides all of these APIs, which are then exposed from very high level through BCC Python module, or there are interfaces through Go or whatever uh, library you want to create. So we did this demo already, and I showed you like this small program how it's working. So now we know that when we do this, it goes all the way through the bpf.so library. When we attach kprobes, it goes all the way down, and then it's able to parse and build the program for you. So you don't have to run Clang again and again from outside. So there's another trace point example. This is static trace point example. So this is not kprobes, but already trace points which are available in the kernel. You can attach to them. So here in this example, I was explaining how you can filter on arguments. You can maintain states also. So this is, I think I was tracing KVM entry and exit here. So this is a uprobes example. So in uprobes is almost like kprobes, but with the availability to attach on user space processing. So with uprobes, you can pay but this is pretty slow because there's a context switch involved always. So you can actually say that for whatever process, for a given symbol, just attach this. So at that time, it's going to like do all of these things. So get the second argument here and probe the read and then print K8. So you have uprobes working there. You have USDT example, which I have just shown here. So in USDT is user space statically defined trace points. These trace points are already there in JVM, Node.js, and all this. So think of them like static trace points, which we saw in kernel, the trace underscore something, but in user space. And you can then attach to those already defined probes, which are there in user space in most of the user space applications. They are, I guess, I've written there in MySQL, JVM, Node, Python. Even so Python's interpreter itself has these static trace points, and you can attach to them. So for example, Node here has HTTP server request static trace points, which you can, and at that request, you can actually get all of this, and you can get the address. So directly from user space. So maps we have already covered what these maps are, but with BCC you have just simple, you just create BPF hash. You don't have to create the complete structure and everything in C. And this gets expanded by BCC to the complete C program. So if you might get confused when you use BCC and see this shady C programs inside, and you'll see, hey, I don't see this anywhere. Because I mean, internally, BCC takes care of completing this, rewriting this C file of BPF to like a more usable. So cursoc.update actually gets written as BPF map update LM, and then with the bracket the name of the current stock, and this gets expanded to actually the complete structure which we just saw, the hash map. So, but this makes it very easy. If you just learn some of these scripts, it's going to be easy to create more and more. Yeah, this was a complex one with maps, where you would read the AX register here, which gives the return value, and then you read. Uh, okay, yeah, okay, yeah. So BPF get current PID. So you read the PID, you update the PID, and then if that's okay, yeah, it's pretty complex. Yeah, it's connect. That's why. So you have to do this because it's a return probe. So it checks whether the current call was actually made in the Kprobe, and this is actually getting executed at the return if the process was there in the map, and then you can read stuff from the socket pointer directly. So you can read this address, you can read the port, you can read whatever, and then you can just print it out on trace print K. So BIO Snoop and all that. So I've written so this is the perf events. So here you create perf event, perf output, which is like events, and you define the event structure. And then when you get the events, you can directly read them in the perf structure, perf event structure. And then when you do perf submit, it sends directly to the perf buffer. So in the backend, this gets expanded to BPF perf submit or something like that, and this completely gets expanded to creation of a map like the with this data and the structure. So yeah, you have BPF get current com, which gives you, I think, uh, some size of the actual programs. So it's the comp from the current data structure in the kernel. So yeah, so you can create, so there's this very powerful tool called arcdist. I think Shasha wrote this. I don't exactly remember. So this tool is able to, so you can literally create a complete histogram by just doing this string, which looks pretty much like what you would do with Kprobe, and it inserts the probe there, and it inserts and returns you a very nice histogram of all the writes where the FD was one, and with size and length. So this is pretty interesting. Yeah, that's all for the presentation which I have. And if you have some specific questions, so you can just ask me about that. There are some papers which I have laid them out here, which were important, and some papers or presentations related to BPF, and some links about all the references which I have used, or you should probably read them. They're pretty nice. There are many products which are coming up with BPF, some new infrastructure which has come up. For example, there is Cilium, which is network and application security in BPF with XDP. So XDP is a very important use case, and there is documentation related to XDP, very detailed documentation, which explains how you can use express data paths to uh, do like more complex event filtering, etc. It will be nice to like go through it once. So
So,
uh,
one question on Hangouts that Sushant asked that he knows that Cilium is used for writing PDF filters, and
yeah.
if there are any other projects to write the same.
So BPF filters.
Yeah.
Okay. So like that's pretty generic. I'll try to explain that. So Cilium is not exactly the only project which is supposed to generate BPF code. It's basically using other infrastructure in to generate BPF bytecode. And what Cilium allows you to do is to insert, to use XDP and the syscall filtering techniques which are upcoming in the BPF, and provide like a network security plane. Okay, and but there are other ways to filter BPF bytecode as well. I mean, if you use classical BPF, you can actually just use the whole BPF string and send it to the kernel, and kernel internally compiles it and sets the filter there itself. So that's not the only thing. There are, I think, multiple things. Can I see the question? Where do I see the question?
Right. So there's a YouTube link that I've shared on Twitter. If you want to open that, is there how it's going? Yeah.
Yeah. Actually, I looked at the Q&A, but it's not updating. I don't know. So yeah, so the easiest way to actually create BPF programs would be using BCC. And for network filtering, there are multiple approaches which have already been tested. And they are like techniques so Cilium is like just a product based on that. But you can have other simpler ways. If you use XDP directly, then you can create XDP filters to drop packets or pass packets. Actually, in fact, like I'll just share my screen. Nice exercise, actually, if you want to try this out. So so I wrote post recently. I went to yeah. So XDP would allow you to do something like this. Can you see the screen?
Yeah.
Should I increase the size? Okay, so XDP would allow you to do something like this, which means that this is at the very lower level driver layer. And what it would allow you to do is to have BPF code at the ingress and BPF at egress, at TC ingress and TC egress. And the packet is inspected at this instance itself and sent to the network stack, or you can or you can just decide to like drop the packet itself. You can even decide to forward the packet to the interface, to this interface or like other interface. I guess with XDP core right now, you can only do it on the same. And this allows you to filter out the packet. So this is an approach. And there is a small example, I guess. Yeah. So there's this small example which you can see, and these examples are in the Linux kernel source tree itself. So we were here. So if you see samples, samples BPF, you would see XDP samples here, and you can see like how XDP is used here. So in terms of XDP, the programs will be very much different. The program type will not be the BPF prog type but it will be in XDP type. And then XDP program will be this, and it gets bound to the lower level interface at the TC ingress, and that's where you would. Okay, where did I put that? I forgot. So and at that interface, you would be able to provide this filtering. So this is I guess the best way to filter at this moment, and you would be able to filter very early. But this requires implementations which are like driver specific right now, so they're not generic. So for generic filtering, you would stick to like TC, CLS in BPF, and and use that to like do traffic classification, like go through that. This is interesting. You can use that to traffic classifier to filter out packets, drop packets, and or forward them somewhere. So yeah, that's mostly what I have for now. Is everyone tired or not?
No, we can go
Yeah.
for other hours. Yeah.
What?
No, this is pretty good. I don't know if
Okay.
anyone has any other questions.
No, but I've got a lot of notes, a lot of things to read.
Yeah. It's pretty massive and it's pretty elaborate right now. I mean, that's what it is. but there is a lot of work being done, and it's like you can say that in at least in networking, XDP would be like the next step of networking, and there are new use cases everywhere. And in terms of tracing, it would be probably like the next stage of tracing, but it's not as evolved yet as other tracing infrastructure which is there. For example, like we worked on LTTNG before, and it's more detailed with a proper format with high-speed buffers, so that you can actually get a lot of tracing data out from the system. So this is to quickly analyze the system, and it does its job perfectly well. I mean, in the situation the scripts are right now with BPF. So you
So
can just,
EBB,
yeah, go ahead.
so this eBPF filter, whatever you have, that can trace also the storage stacks as well. The file
Pardon,
system.
I didn't get.
The storage IO stack. It can trace the storage IO stack as well.
Yes, it can. So as I explained, it's Kprobes. So with Kprobes, you are able to look at all the paths in the Linux kernel. Okay, and this also includes the IO stack as well. And uh, as I was showing you here, where is my thing gone? Like, so as I was showing you in IOVisor BCC, I think Brandon Gregg has already given a very nice diagram which tells you like the whole stack, which includes the block devices as well. So block IO top, block IO snoop, block IO latency. In file systems, they have ext for dist, ext for slower. So all these tools are able to identify through file systems. At VFS layer, which is like top, so you can do open snoop, stat snoop, sync snoop, VFS count, VFS stat, pretty nice. File top. Okay, so you can actually right now with this mechanism and the scripts available trace almost all parts of the kernel. And then some programs which are generic, they can trace almost everything, like trace, which we saw. If you can just trace any function which you know.
So there's a systems library section in there. But
Yeah, here. Get
So-
host latency memleak. Yeah.
So what exactly is that? When you're talking about get, are these probes that have been written, or
Yeah, these are tools that have been written. For example, let's look at memleak. Okay, so these are all parts of these tools in BCC, and we can T, yeah, tools. Yeah. So you can see memleak. So what memleak does is it attaches to mallocs and frees in a given process, and it looks at like all the allocations, and if it sees some weird allocations, it's going to the top two stacks with outstanding allocations. So it prints them every certain amount of time, I guess. I don't know. Traces and matches memory allocation and deallocation requests and collects call stacks for each allocation. Okay, so this is nice.
so
So
malloc and
what?
free? And
What?
how does it work for malloc and free?
How does it get malloc and free?
Yeah.
It uses, so my guess is it uses the uprobes or USDT inside the glibc direct. So we can see it here. So it must be opening libc somewhere. This is my first time looking at this tool. I didn't follow it. So where are they making the probe?
So we have user space probes.
Yeah.
That we added for system tab.
Okay, so those probes will work here, because if those are static user space probes, then they will definitely work here as well. Okay, actually, yeah. So they have both the techniques. If you are using if you're not using the kernel trace, then it attaches the uprobe to malloc symbol, and I guess in obj, I don't know what that is. It's glibc definitely, and then if you are not using that, then it tries to go to the kernel and like not tries to. I mean, it goes to the kernel and looks at the kmalloc and kfree. So if you want to look at the kernel side, you use this. If you want to look at the user space side, you use uprobes.
So this is actually looking for a symbol, right? It's not looking for user space probes that have been added.
No, this is uprobes. So uprobes, it's looking at the symbol, exact symbol. So
Right.
if this can definitely be so if someone of you are interested, so you can update this or write another one which uses USDT probes instead of uprobes. And I think there are some USDT probes as well somewhere. I don't know, like
May I
hold on.
ask, there are a lot of other probes within glibc that we added for system tab.
Yeah, okay. We are going to do tools for them.
Yeah, so my question is, are you going to do those tools for them?
Okay.
Would you be, as in, I'm not saying you as in you, Suchakra, but
Yeah, definitely. I mean, if we propose like so what I can see is that we can definitely have like a section of tools dedicated to libc. Okay, so it will be like a new library for libc, and inside, for example, see, people have added tools to identify flow across Java, Python, and programs. So if you see like flow example, you can do this. You can do this, like literally all flow across UB programs or flow across Java programs directly from BPF. And this is done by inserting probes on method entry and method exit in Java. Okay, and if you do that, you are able to do that. So what we'll do is we'll have programs like this which use USDT probes, and those probes are inserted on glibc's standard, like the static trace points which are there. So here they are putting on method entry and method return. So there we'll have whatever static probes are there, and then we'll read the arguments for them. Okay. How do I stop this? Yeah. Any more questions?
no, I think we're done.
Okay, it's pretty late there, is it?
It's 8:30.
Okay. So
Stop the broadcast and then we can continue.
yeah.
So is this recording?